Good afternoon, everyone. My name is Wang Dazuo. I'm a professor in the Architecture Engineering Department at Pennsylvania State University. So this semester, we are having our guest lecture series on advanced modeling for building and community energy systems. So today, we are kicking off this series with a special guest, Dr. Michael Waiter from Lawrence Berkeley National Laboratory. Almost 15 years ago, Dr. Waiter starts the Modelica Buildings Library, which now grows to a big community working on Modelicas. So today, Dr. Waiter is going to introduce the most recent research at Berkeley Lab on how to use Modelica for buildings and district energy systems. So the floor is yours, Dr. Waiter.
Thank you very much for the introduction and the invitation. So I'm going to present how we use Modelica for applications in energy systems at Berkeley Lab and motivate that with a current project that we have been executing that really illustrates how we use Modelica to advance that particular design of an energy system. And that's just one of the many applications that we are doing at the Berkeley Lab in that area. So the question is really, how do we transition from today's bespoke, increasingly complex energy systems to high performance, reliable systems at scale? And then specifically, what is the role of Modelica within that transition? And on the left-hand side, you see steam heating and power plants at different university campus that really illustrates that those systems are typically installed ad hoc and have an immense complexity. And we really want to break that down and simplify the design of those systems using platform-based design so that we have a larger use of components like you have, for example, in the automotive industry as one particular application domain. So the main talk is really around complexity. So complexity in terms of design, of how we design those systems, how we control the systems, and then how do we get those designed and deployed systems into industry at the scale needed to address the transformation of the building stock toward high efficient, renewable, resilient, and energy secure systems. So in terms of design, you see here two Sankey diagrams of a project that we executed for the Department of Defense, Joint Base Andrews. So it's a military base outside of Washington, D.C. On the left-hand side, you see the Sankey diagram with the annual energy consumption for a system that uses gas heating and air source chiller. So it's kind of business as usual retrofit. And we have two coupled systems here. On the right-hand side, you see the Sankey diagram for the energy flow, again, for the whole year, for the same base, but now using a geothermal coupled thermal energy network with PV and battery. We have about 25 coupled systems in there. And so it's a significantly higher inherent complexity, but with this transition, we are able to reduce energy reduction by 70%, cut on electricity peak reduction by about a factor of 2. We don't need to maintain the gas network anymore, and we have only about 20% increase in life cycle cost. So the question is really, how do we manage this immense complexity now, and what kind of design tools do we need to put in place to design them in a reliable way and be able to deploy them and operate them in a robust way? And that really demands new processes and new tools compared to the much simpler system that you see on the left-hand side, that you typically design with a standard back of the envelope calculation or spreadsheet calculations as an example. Similar on the HVAC control side, we have been looking a few years ago into complexity of control sequences that published by ASHRAE for variable air volume flow systems. So ASHRAE published sequences about in 2006, about 20 years ago, and then updates those sequences about 20 years later. If we implement the same sequences in Modelica here and count the numbers of lines of code, we see that we have an increase in numbers of lines of code by about a factor of 8. So we have significantly higher complexity just for a simple HVAC control that saves anywhere between about 15 to 30% energy, depending on the climate and the load variability, etc. And the interesting part is if we overlay this complexity now to the number of lines that we see in military fighter jets. We see a similar, if not a larger increase in the complexity in building controls. And of course, those planes, they are not designed anymore on a rice board without verification. So the whole design process has been changed. And we are really interested in how do we need to change the design of those advanced energy systems so we get them reliably to scale. And for buildings, we are happy that they don't fall from the sky like an airplane does if you design it wrong. But we still need to be able to really get them implemented in a robust way at the scale needed to transform the building stock. And if you're just looking at the scale of the problem, if you retrofit all buildings in the US in the next 25 years, so by 2050, we talk about retrofitting about 10,000 buildings every single day. And there's just not enough knowledge yet how to do deep retrofit at scale, and today's process has shown to really fall short in that. In dense neighborhood, the thermal energy system, as I'm going to talk about afterwards, are very promising here to improve energy supply security, resilience, and compress cost. But again, how do we do that effective, reliable, robust, and make a dent here in the building stock, given this increased design and operational complexity? So essentially what we're asking today is designers and owners to carry the risk of using proven technologies or proven components in unproven configurations. So if you're looking at those energy systems, there's nothing new in terms of their components. So they use heat pumps, chillers, heat exchanger, pumps, etc. But the way how we use these components in a new configuration, that system integration is the new part, and we need to be able to manage that risk here. The way we mitigate this risk here is through three pillars. So the overarching framework is platform-based design that defines the process that we are doing. Within each of these design layers, we use model-based engineering to verify performance versus requirements and embed that in a highly digitalized workflow so that we can actually look at the dynamic behavior of all those subsystems. And that really leads into this innovative system integration. So the overview of the talk is really talk about the motivation in terms of complex design choices. We need to de-risk the integration of these proven technologies or proven components in new systems and do that at scale. That brings us to a new design flow called platform-based design that we transformed from other industry sectors like electronic design automation and automotive industry to the building area. Underlying to that is modular design so that we get a high degree of reusability of components, where a component can be a whole energy transfer station. And then platform-based design has a clearly defined layers of abstraction where you successively refine the design. And within those layers, we conduct model-based design. And the underlying computing technologies that I'm covering here is quickly the mixed integer linear programming for design choices. So that's not a focus on the talk. But afterwards, I'm going to talk extensively about Modelica for de-risking and then for digital control delivery, which are really the key technical parts. But first, I need to talk a bit about modular design so that we can get an increased degree of reusability of components. And the question here is really, how do we get the modularization in district energy systems? If you're looking at the automotive industry, those cars are very heavily built around modular designs that are then used for different product lines within a company, but even across different automotive providers. And the question is, how do we get to this modularization and reuse in district energy systems? And we devised 3 levels here in terms of this modularization. So the first is to move from equipment to modular energy transfer station. And the layout that you see on the right-hand side is a schematic diagram where you can plug in then components like heat recovery heat pumps, bore field, energy storage. And if you basically follow this pattern here, we know that the system itself works efficiently. Using then this energy transfer station together with other components, for example, heat exchanger for sewage heat recovery or cooling towers for free cooling or centralized geothermal bore field, we can compose them into what's called a reservoir loop. So that's a network topology that we introduced in 2020 in the paper that's cited here. And that allows us now to modularly plug these components in and guarantee that we have no influence of this different transfer station in terms of the water distribution and pressure distribution. So we can start expanding that within a network. And then this reservoir network can be meshed up to reservoir mesh, which we also introduced in 2020 to successively build out the district as funding becomes available. So with that, you really have this basic building block that you can move from individual energy transfer station all the way to districts and do that successively as funds become available. This modularization is really critical because at the end, we want to build up libraries of these component models so that we can get a high degree of reusability that continuously improve this performance of these components and cuts down design times through this high degree of reuse. That's orchestrated then within this design flow called platform-based design that I explain based on the work that we did at Joint Base Andrews. And first, I'm going to just talk about the primer for platform-based design in a couple of slides. So the key underlying part of this platform-based design is really that you have clear separation between functional requirements. So what the system ought to do, for example, heat, cool, and power buildings. And it needs to do it, for example, at a certain cost within a certain budget. And there are energy regulations, for example, that it needs to satisfy. And then on the right-hand side of these bow ties, you have architectural components. So you can heat a building, for example, with a gas boiler. You can use it air source heat pump at that building. You can use a thermal energy network. You can substitute also some of the grid power with PV or battery. So you have a choice of different architectural components that you choose from in order to meet the functional requirements at a certain level of abstraction. And then when you make a binding between the components assembled to an architecture that fulfills those requirements, you have a candidate system that is then moved into a next layer of abstraction. So you start refining it and do a more detailed design. And so that you really get freedom from choice. So you basically restrict the design space as you get closer and closer to implementation, and so that you manage the inherent complexity of the design process. So that's a process that we explain in this applied energy paper from a couple of years ago, in which we transferred that from the electronic design automation, made a small demonstration for the strict energy system, and we built that out now to use at a much larger scale for this Joint Base Andrews. Specifically for Joint Base Andrews, we have, for example, functional requirements in terms of life cycle cost, investment cost, but we also have hourly cooling loads that we need to meet at every hour of the day. We have restrictions on maximum peak power. Then there are some other harder to measure requirements like simplicity of maintenance. And then we have different architectural components. For example, we can provide gas heat and chiller for cooling, or we can use building level air source heat pump or building level geothermal coupled heat pump, or we can have a geothermal thermal energy network, so the TEN. We can have PVs and batteries that we can combine to any of those systems. And once we pick a certain solution, and let's say it's the green components here, they're going to be moved down to the next level of design. And now we have requirements that flow down from the top level, like life cycle cost, but also additional requirements that become active now because of these components that we have been using. For example, because we have a thermal energy network, we have a maximum service line temperature. So in the distribution network, we have requirements on heat pump cycling rates, also requirements on maximum storage tank size. And again, we have different architectural components of how we can meet them in terms of bore lengths, heat pump selection, hydronic systems that we can choose from, etc. And if you don't meet the requirements, then you may have to do an iteration up the higher level and refine some of the assumptions that you have been doing above. So you get immediate feedback here within these design steps, and through that maintain the performance and verify that at every single step here, so that if you don't meet the performance, you know that a priori before you get to actual operation of the system, in which case it would be very expensive to fix some of those design shortcomings. So for Department of Defense at Joint Base Andrews, we have these platform layers where we start with DoD, the Department of Defense policy and guidelines. So those are some high-level requirements. Then we went into a system selection. Afterwards, in a detailed design and verification where we de-risk the system, and did a manufacturing and installation layer on the bottom that we start basically setting up, but we have not yet executed this part. The way we execute that is at the top level, we have certain policies and guidelines that led us then to a recommendation of 4 different candidate systems. So at this point, we just talk about those type of system that I mentioned earlier, so the gas furnace with chillers or the distributed heat pumps or the geothermal energy network. We have not done any design or any sizing at that point. It's just putting up the design options, and we identified, for example, where a thermal energy network could be, where would be a central plant for a bore field. So here was, for example, a discussion, can we do a bore field, or can we do an aquifer thermal energy storage, or do we need other storage technology, just to basically start constraining the design space to what's practical for that particular site. In the next step, we went into system selection. So now we developed the schematic diagrams that are needed then for providing or developing cost models. And we developed the linear or piecewise linear models here for techno-economic optimization of these 4 candidate systems. So we followed the so-called energy hub principles that was developed at EMPA and ETH, where we have energy buses, for example, for providing heat, for providing cooling and electricity. You have transition components, for example, a heat pump draws energy from the electricity bus and it produces heat in the heat bus, and it also takes heat away from the cooling bus. So those are energy transfer components that are characterized with efficiencies. And then we develop the cost models for these different configurations so that we can stretch up and compute the cost depending on different equipment sizes or component sizes, where a component can be a whole energy transfer station, or it can be a size of a PV installation. Doing this mixed integer linear programming, we looked at millions of different design variants and developed these Pareto optimal solutions here, or those optimized solutions that are shown on this lower part of the graph, where we contrast and optimized annual life cycle cost and imported energy as a matrix for energy supply security. So any solution on this dashed line is Pareto optimal, so you cannot reduce life cycle cost without also increasing imported energy. And what you see here is that, for example, the blue solution, the gas system, if you start adding PVs and battery to the gas, you get some improvement here, but you don't get the savings that are needed to meet the requirements that are shown in this green rectangle. So you really need to have a system change to a different system topology and then optimize that system further. And that's what we were doing, and mixed integer linear programming allowed us to do coarse enough models to do this optimization in a computationally tractable way and identify what are the trade-offs of these different systems. Out of that, we picked then for further refinement the thermal energy network with PVs and batteries. So the lowest red dot here that is still within the green box, so that meets the requirements on life cycle cost and on imported energy. And this solution is then refined and de-risked in the next step. So at this next step, we developed and refined further the schematic diagrams for these solutions. We developed the control sequences, first the usual way in terms of writing down detailed sequences of operation. Then we implemented those control logic together with an energy model in Modelica and did verification using now a prescriptive model that couples mechanical, geothermal, and controls system together. And that was critically important, as you see in the future slides, because without this verification step, we would have grossly undersized the heat pump in the central plant and missed the optimization opportunities that were about $2 million just in first cost that easily paid for the study itself. So now having this detailed model available, we did data-driven techno-economic optimization of this particular design and identified, for example, opportunities to reduce investment here by close to $3 million by doing some performance-based contract on maintaining the strict loop temperature within a certain numbers of Kelvin hours where we violate the loop temperatures by about 18 hours a year. So 18 hours where we violate the temperature by 1 Kelvin allows you to downsize the heat pump and save about $3 million. So that by itself was easily paid for the study. And in the next step that we set up now in the study, but have not fully executed yet, but we executed all the necessary steps here in other context here, would be then to move toward digitalized construction workflows where you use this model that is not just a representation or an emulation of the anticipated behavior, but is a specification of how to build the system. We use this model. We can then export verified digital control specification following an emerging ASHRAE standard 231 that should become a public standard early next calendar year, and follow the process that we developed in the Open Building Control project, where we then export a point list, control logic, and semantic model, and then semi-automatically configure the control system and the configuration of the communication system together with energy information systems and fault detection diagnostic methods. So that really provides a basis for moving toward digital twins during operation. So you're going to hear about those aspects all in the subsequent slides. But just to summarize, the outcome is really of going through this process is about 70% energy reduction, about half of the peak electricity usage, even though we have a fully electrified system now, that we don't need to maintain the gas infrastructure. We have 20% higher life cycle cost only. We identified $2 to $3 million investment reduction, in addition to about $300,000 per year life cycle reduction, and demonstrated this process for techno-economic optimization and de-risking of the system integration is really feasible and should be something that we want to invest further on with validating it at other sites. So the next question is really that we saw these Sankey diagrams of annual energy consumption of the gas solution on the top and the thermal energy network on the bottom, which just is inherently more complex in order to achieve this higher resilience and energy security. But the question is, how do we get that now to an implementation and de-risk the design of the mechanical system, the geothermal systems, and the control, and realize when we need to make design changes before we operate the system, when it would be prohibitively expensive. And of course, the top part, the gas solution with air source chiller, you can design that in a spreadsheet in Excel, for example. But you're not going to do that in the lower part anymore because you have this coupling between the different subsystems, and operation becomes really critical here to achieve the performance. And the question are really, how do we meet now requirements at the design level in terms of energy costs, no more than about 10% of what we predicted in the optimization. We have now cycling rates of the heat pump that we need to maintain. We need to maintain service line temperature of the distribution line, which the mixed inter-linear programming had no notion about these temperatures, but now we need to make sure that we actually can maintain them. And then the operation needs to be practical and taking into account that we have a real digital representation of the system that doesn't have perfect knowledge of the future like the optimization had. And it has much more realistic physics implemented that MILP did not have. So that brings us then to the design and verification with Modelica, where we really de-risk this solution that is proposed by the mixed inter-linear programming. And to do that, there was really a fundamental change that I advocate of how we should be using models. And it's fundamental change for the building industry, but it's exactly how other industries like the automotive or the chip industry is using models. And what Edward Lee, so a professor in Berkeley, basically said that we can either create a model that is faithful to the system, and that is basically what the scientist is doing, or we can build a system that is faithful to the model. And that is what an engineer should be doing. So we should basically build the system according to how the model is being how the model specifies it. And the first part is basically what we do today in our building industry. We start with a blueprint. Someone builds a system, someone else creates the model of this design. That is a descriptive model. It's used to understand the behavior, and it didn't really address managing the complexity of this system. I think we should turn that around, that an engineer should create a model that serves as a specification. That now becomes a prescriptive model. So it says how you operate and how you build the system. And then you need to build a system that complies with these specifications. Because without that, you just don't know whether the system is going to work. In particular, if you move toward more dynamic systems that are grid responsive, have energy storage, need to trade off thermal with electrical energy, for example, to address grid constraints, etc. So that's really fundamental change that we think we should be doing as an industry. So we demonstrated that now in this de-risking step, where we started with a schematic diagram with all the control, which is now very simplified for a very small system here. We implemented a nonlinear dynamic models for design and verification of this optimal selected solution with MILP. This model then serves as a digital construction specification and is also in a way that we can export digital twins for operation using these emerging ASHRAE standards. And that really brings us to the technology in terms of Modelica and the motivation why we use Modelica extensively in this project and also in other ones. And Modelica itself as a language is really an open standard for dynamic modeling of engineered systems. So it's used not only in building industry, but originally was developed mainly in the automotive industry. It's used by aerospace industry, and pretty much all the industrial sectors are that exist use Modelica in one way or another. Systems are represented then by differential equations, so that's important for modeling energy storage, PI controllers, for example. We can also implement algebraic equations, for example, for pressure-driven flow networks, so we can compute pumping energy consumption in our district network. We have discrete equation for control switches, and that really allows us now to do a simulation of the actual control, the thermal system, pressure-driven flow networks, and look at dynamics from sub-seconds, that is important for some of the control, all the way to years for the geothermal storage, all coupled in one model. And using the Modelica Buildings Library, we developed with about 50 contributors at the Berkeley lab and all our partners here, the Modelica Buildings Library. That is about 3,000 component models and functions. And models range from the detailed controls to HVAC system, buildings, electrical system. It's used, for example, by major HVAC manufacturers, by design firms, and also by hyperscale data center providers are using it to design data centers and in some cases to operate data centers in real time to take into account future loads and weathers. All components are validated and documented, and since a few years it's the most cited paper in the Journal of Building Performance Simulation. So it's extensively used in the research community and increasingly now also in real applications here of diverse HVAC applications. So the Buildings Library has some comprehensive set here of district energy models, so we can model all the way from first to fifth generation system. We can couple it to AC and DC electrical system models, so that opens us now an opportunity to look at sector coupling between electrical systems and thermal systems. There are models for different building loads, ranging from detailed energy models with energy plus simulations to reduced order models or just time series. We have all the different network topologies, so 1-pipe, 2-pipe, 4-pipe, and steam heating, and storage technologies, for example, for geothermal boreholes or bore fields. We have aquifer thermal energy storage. There's models for water tank, or you can couple it with detailed geothermal simulators like the TAF simulator. Using now this Modelica Buildings Library, we implemented then models according to these schematic diagrams that serve now as a means to verify the performance of the system and serve also as a specification for how to control and eventually construct the system. So those are now prescriptive model that we implemented, and you see here that it's really true to the implementation. So the bold blue lines on the right-hand side are the fluid lines that you see, the same lines on the schematic diagrams, and on the top, these various lines that you see, those are control signals, so sensor signals, and then actuator signals that open and closes, for example, control valves or control the speed of the pumps. Then doing this system simulation that contained all the components from energy transfer station to the central plant and district energy system, we checked compliance with the results from the actual site. So what you see here on the first column, the site is the requirement, then what we achieved in the mixed integer linear programming. And with Modelica, we have similar performance now as we have in MILP. But we have to say that there was one iteration step needed because in MILP we grossly overestimated the bar field capacity because we used literature data which were just not applicable for this particular design. We did then one more iteration on the MILP optimization, and then after that we have similar performance now between those two approaches, but they use completely different models for calculating those performances. The only requirement that we violate is the total investment cost here, but we indicated if we centralize utilities and do a privatization of the central plant and the PV and the battery system, we actually have lower investment with the thermal energy network compared to the gas and the gas heat and the distributed chillers in each building. So the associated financial business model is also important here to get that to an actual installation. We also have guiding values, for example, between coefficients of performance and capacities of the different components. And also here we have a good agreement between MILP and Modelica, so that really gives us confidence here that we did in the optimization eventually do the right assumptions here after we corrected the bar field capacity and also corrected some capacities of the heat pump. So now we have a good agreement here between those different levels of abstraction. So now this specification is clearly documented through schema and digital models. So we have on one side a schematic diagram that served us as a first step to build a model. We developed control sequences in English language, like the insert that I put here, which is just one part of a central plant control that we then implemented in that Modelica model, which is now the specification, and that was used then to validate the system behavior at the whole thermal energy network level. This de-risking was really essential here for reliable and cost-effective installation. So there are 5 points that I list here where we basically saw that our initial design was just wrong and didn't work out. And the first point was that the bar field heat transfer and central heat pump was overestimated in MILP because we used literature values for heat extraction rates. They were just not applicable given the dynamic operation of the bar field and the small temperature differences that we had in the reservoir loop. So we corrected here in the de-risking step this design here using the actual heat transfer rates that the geothermal model in Modelica reproduced and reused that in MILP to do one more iteration step. Then the bar field seasonal thermal management here also didn't work out first. So we didn't achieve the performance that we needed from the bar field on an annual basis. That led us to do a correct that through a complete redesign of the central plant hydronics. So we basically did all the piping and the valving in the central plant that you saw before. We had a different implementation that turned out to not perform as required to meet those performance. Then the central plant and the district loop control, we tested 3 different implementations of the control sequences. So we wrote them down in English language first. We reviewed them. We also looked at it with mechanical designers. They looked fine. We implemented it, but we observed, for example, heat pump cycling. We didn't track the district loop temperature. So those are very dynamic responses here. And the third implementation then of the control sequence is now such that we can verify that it meets the requirements here. And for that, it was really absolutely essential to do a fully coupled simulation of the control, the mechanical system, and the geothermal bore field. The energy transfer station control mistakenly flushed the buffer tanks. So again, we lost performance there. And heat pump temperature reset had to be changed because it was unstable in the beginning. Again, we corrected that control, so this de-risking step here. And in the central plant economizer, the simulation basically showed that this equipment is just immaterial for that particular climate and can be removed to save investment cost. Even though that's a component that's very common in the strict energy system in other climates, but for this climate and this operating temperature, it's just not worth the investment. So doing those changes post-constructions, if you wouldn't have done the de-risking step, that would really cost several $1 million. It would take multiple years. It takes years to recover from a wrongly managed bore field, if it's overheating or overcooling. And so that risk reduction was really critical here, and it paid easily for itself. Sensitivity studies were then also conducted, as I mentioned earlier. So now we can use the model and play with different design variants. So we can see what happens if we reduce or increase the heat pump capacity in the central plant. And what does that do to the investment cost or to the life cycle cost? And here we identified a cost saving potential of around $3 million by undersizing the heat pump a little bit while still maintaining the loop temperatures except in 18 Kelvin hours over here, which is really a very small amount. On the bore field performance, I mentioned earlier that it was essential to couple the bore field model with the mechanical system and the control. And just looking at the 2 days of operation here and the heat flow rate between the heat pump in the central plant and then the bore fields. And we have 2 bore fields. So a perimeter bore field for the daily swings and a center bore field for seasonal storage. You see these large variations of the bore field depending on whether the bore field is needed to stabilize the loop temperature or whether it's being activated, for example, and cooled, in this case here with the central heat pump. You get these huge changes in heat extraction rates. And if you look at the frequency diagram on the lower right-hand side here, that shows just for the spring, for the center bore field, that we have heat extraction rates between -40 and +40 watt per meter. So that was the initial value that we used in the MILP optimization, which was suggested from the literature. And during operation, we almost never get to that performance. So that was really critical to learn from the detailed Modelica model what the actual performance is, put that back in MILP, and see what it does to the sizing of the equipment and to the whole techno-economic optimization. So without that step, we would have wrongly designed that system. So platform-based design was really critical here to achieve efficiency and de-risk the design. We had this 70% energy reduction and about half of the electrical peak demand here, and we de-risk the system integration. It easily pays for itself. It's a cost reduction of more than $2 million investment reduction that we identified, in addition to about $300,000 annual life cycle cost reductions, and then design flaws that would have cost way more, probably several $1 million to correct if they would have been detected only during operation. And the key part is really that this one is a systems opportunity. So the major performance gain does not come from better components, but it comes from the integration of these proven components in new system context. And that's really what needs to be improved and de-risked with a robust workflow. The last part of the talk is really addressing how do we get now digital control delivered. So how do we get this performance in operation by translating the verified control sequences from an energy model to the actual building automation system? And how do we use now this model to create digital twins that can be used during operation? For this work, we build on about 10 years of development that we did in the Open Building Control project, where we developed a workflow and technology that allows us to export models of the controls from a subset of Modelica implemented in control product line, and then do a formal verification of the as installed sequences, trended from a billing automation system and verified against the computational model from the design. That is based on this digital representation that is now being standardized through ASHRAE standard 231 or control description language. That's a standard that is expected to become public early next calendar year. And that's really the foundation now that we are using for this translation. And this standard is built on this open billing control project that we developed starting out 10 years ago. So control description language is a subset of Modelica, and it's basically a minimum subset that we think is needed to implement the billing control sequence in a block diagram language. From there, we can translate then this subset to what we call CDL JSON, which is a JSON LD representation that makes it easier then to translate from that representation to actual control product lines, and also to export, for example, semantic model according to the ASHRAE standard 223P, which is also in the final review and expected to be released, I think, next calendar year. And using now a subset of Modelica allows us to go this deployment path toward existing control product line, but because Modelica itself is an open standard with a large ecosystem of tools and code generators, next generation control product lines can also directly generate, for example, C code or generate code in other languages, or they can use the FMI standard and the SSP standard, or you can use eFMI, which has been specifically developed to run Modelica code on embedded system for real-time operation in critical applications. So there are different ways of addressing existing control product line, but we can also address a new generation control product line, which is future-proof code generation using a variety of existing open software standards. We are working now with several control providers on the translation from CDL to their control product line. So for example, with Icon, so it's a carrier corporation, with Normal, with KTC, and also with Tridium, which is a product from Honeywell. We work with them now on how to translate these control sequences to actual implementation on their control product lines. We did a proof of concept for that with automated logic. So we implemented the Modelica model here based on the guideline 36 for a VAV sequence, and translated that then to automated logic. So what you see in the middle of the graphic here is a subset of this control sequence, and with two PI controller on the top, and you have the same controller then translated in the ALC implementation, and then you have this nested controller, for example, for the damper controllers. The vision is, of course, that now for our district energy application, we have these control blocks, again, for the district energy system, which follow also this ASHRAE standard 231. So we can use the same machinery then to translate this control logic to the respective billing automation system that eventually will be selected for the installation. In addition to the control logic, we can also export then semantic models, so following the standard 223P. So there are some means for adding annotations to this Modelica model in order to export then the semantic model. And that really complements then the ASHRAE standard 135 or BACnet for communication. So the BACnet basically deals with the communication of controls signals. Standard 223, the semantic interoperability, specifies a topology. So for example, which air handler unit serves which zone. And this topology can then be used to semi-automatically configure the control logic that's exported according to the standard 231. So those are all complementary and really are a major step toward the cost reduction in deployment of controls or automated fault detection diagnostic methods using those ASHRAE standards. We demonstrated some of this automated deployment with partners in Denmark, where we basically used the Modelica billings library. We assembled the subsystems, for example, a heat exchanger for cooling coils with the valves and the temperature sensors. exported those subsystems as a functional mockup unit. So that's a computing unit that conforms to the functional mockup interface standard. We had the component signatures in terms of parameters, for example, that allows us then to combine them with semantic model of the buildings. And then using this combination from semantic model and the component library, we can do a high degree of code generation to create the simulation models that are then combined with real-time data. So a database that's fed with measurement devices from the actual buildings. And then using estimation methods here, we can identify parameters and look, for example, parameter drifts and use that as a part of a fault detection diagnostic method. So that really opens up now for digital deployment of the controls, but also for digital twins using the combination here of these control realistic component models from the buildings library that can be used to assemble different subsystem models and combine that with semantic models that represent the topology of the installed system. So to summarize here, platform-based design really allows us to move progressively here from a very high level of abstraction in terms of energy system configuration to MILP optimization and then de-risking here within these clearly defined platform layers. And it's really a meet in the middle process where we align top-down requirements with the bottom-up implementation constraints to come up with feasible designs. That allows then high component reuse via this modularization, which is important for the next step then in platform-based design to actually build up those component libraries, mature them to reduce design time in subsequent studies. It allows us to do a verification against requirements at every stage of the design process. So we get the feedback already very early on to see whether we can meet the customer requirements in terms of energy reduction or cost budgets. The models now serve then as a specification at every layer here. So MILP specifies how to size equipments on Modelica level, and Modelica specifies, for example, how to control the system. And we have then a feedback here within these platform layers, if you can't meet the performance, and also within future versions of these component libraries. So if we build a system and we learn out of actual measured data, we can feed that back into our design representation to successively improve how we represent those systems. Going through this process allowed us this drastic reduction in energy use here at Joint Base Andrews. So we cut down energy by about the 70%, half the electricity peak reduction, despite not using any gas here. So we can also have investment reductions on no longer having to maintain the gas network. Modelica itself was strong here for de-risking this coupled control HVAC and geothermal system, which was critically important here. It really provided the flexibility to model this proposed mechanical and controls design as it would be implemented in a real system. So we weren't constrained by the tool having certain physics in there because it's a freely programmable environment. So we can really represent the energy system at the level of detail that we need for that level of verification. And then it provides a path for digital deployment using those emerging ASHRAE standard for the controls and for the semantic model. And that's really then a basis for digital twins in which we create those models and adapt then the model with real-time data. And key for that is really, in my view, that we as a community in the building industry change how we use the model, that models really should serve as a specification and becomes a prescriptive model, and then systems should be built to comply with that particular model, as opposed to building something and trying to do a model on the side to see what's the expected performance of the system, because that has not served us very well in the past, and it's not going to serve us well in the future as those systems become more and more networked across different energy carriers and need to be grid flexible and serve much more requirements in the future. So with that, I'm happy to answer any questions that you may have.
Anyone on site, any questions? Yeah, maybe Mike, you pass them. We will have one microphone, right? Okay, maybe you can speak here.
Okay, I have a question about, as you said, like creating models that are prescriptive for how we construct and design future systems. One criticism that I get over and over is that my models are not validated adequately. So there's not enough data to, like, even if the components are validated, the subsystems or the system itself has not been validated against data. And so how can you defend the results of your model or know for sure if the model can be implemented in the real world in a feasible way? So like, how do you respond to that?
Yeah, so I would say a lot of the models also have been validated in a system context in various papers. Of course, there's always variability from the construction that will impact, for example, the performance. And one example that's just on top of my mind is, for example, the fan performance. You have the fan performance curves from the manufacturers. Those are in a model. And those models represent really this performance curve well. But now if you implement this fan in a real system and you don't have a straight inlet of the fan or straight outlet, you get turbulence that affects the performance of the fan, and your equipment performance data from the manufacturer, which are part of the model, are wrong basically for that particular situation. So here you need to be careful that the system is implemented correctly, or if you anticipate things like that, make sure in a model it's also represented accordingly. But I think doing that in a somewhat semi-controlled way, semi-controlled because you have limited data available, is probably still better than just building something and hoping it works. So at least we have feedback, we do the best we can here in terms of specification. In other industry, the way I understand it, for example, this design industry, electronic design industry, and also car industry, if you build a subsystem of a car and it does not meet the specification, your design is not, or your product is not accepted, you have to fix it. We are far away from that in the building industry, but I think we need to get closer and closer to actually being able to construct something according to specification in a model. You can always add some safety margin, for example, see what happens to your performance if your heat pump COP is, let's say, 20% less efficient as you anticipate from the manufacturer data because of local insulation or because of not enough refrigerant charge or whatever the underlying cause is. But at least now you have a means to see what's the effect of not meeting certain criteria when you implement and build the system, and get a feedback from that and can make an informed decision whether you can accept this type of robustness. Ultimately, it would be great to also add uncertainty to that part, but that's something we are not there yet, basically. But that might be another way to start design for uncertainty and robust design. That adds another level of complexity then. But I think that would be a first step here, to do it deterministic and then start to see how you could expand that with determinism, with stochastic models. Yeah. Sure.
We do have quite a good number of questions from online. Michael, you may start from one by one. This is the first one from Daniel.
So what's the status of open source Modelica tool versus proprietary tools like Daimola? Yeah, so we keep working with the open Modelica developers here to get more and more coverage of the buildings library. We are really constrained in terms of the funding, what we can do here. So we do the best. We test our implementation, our library against Daimola, open Modelica, and Optimica, so the engine in Model on Impact, and try to have coverage in all those tools. We know that also Wolfram Research is testing our libraries, and we address feedback from them as we get. So our goal is really to have as much coverage in all these different tools, but at the end we are constrained basically by the funding that we can invest in that area. So for platform-based design, could you please speak to why MILP versus other design space exploration have been used? Yeah. So platform-based design is agnostic about the method that you're using here. So we could have used any other optimization in there, or do a lot of, or build every system itself in Modelica and contrast them that way. That's really now art of how we populate the platform-based design with what kind of models and what kind of level of detail do we need to follow here. So we have other projects, for example, in a data center where we also use platform-based design. Here we don't use MILP, we use nonlinear programming for that part because it's a different problem area. And we use a completely different software for that. So that's really now the knowledge of the engineer or system integrator who sets up this platform-based design to make a decision of what kind of level of detail do I need to use at these different platform layers, what models is fit for the purpose here, that gets me to a reasonable solution here with sufficient accuracy or trust, and also that's defendable in terms of the labor time that you need to put in here. And MILP, in our case, we used it because the software that we are using here, Symphony, has a lot of pre-configured system. It has a good implementation of this energy hub principle, and that's basically what we ended up using then. But you can use any other method here, whether it's another MILP method or nonlinear programming. But the key part is really that we advocate at that point, don't start with the Modelica model, because developing the Modelica model was very labor intensive, and you don't really need that level of detail for the high level decision whether you go with a gas heating or with a thermal energy network. So that's why you really need to use the simplest model that's fit for the purpose to answer that particular question. And then you de-risk it afterwards in the next step. Yeah, so I think, so there's not yet automate between MILP and Modelica. So that's thing that we are looking into, how to automate that. And we try to get more resources in that area. I think there's really a huge potential to automate that in future work here. And JBA, our understanding is that they're proceeding with a small demonstration here, not the whole 17 building that we looked at, but a smaller demonstration to prove out the installation here, together with other feasibility studies at the Department of Defense. And then about the zone power field model. Yeah, so question is whether this zone power field model has been validated, and we did do a comparative model validation against FeeFlow. So FeeFlow is a finite element method tool that's heavily used in geothermal application. So it does a detailed 3D heat transfer. We implemented or worked with another company here, Respec, who implemented zone power field model in FeeFlow. We implemented exactly the same in Modelica, used the same boundary condition, and we really match pretty much almost exactly the result from FeeFlow. So the short-term behavior is a little bit more accurate in Modelica, and the FeeFlow documentation actually points out that the numerical method that they're using is not applicable for very short time response, so a lot of minutes, if I remember right. But once we are past that, we are pretty much on top of the FeeFlow results. Key is really to understand what your geothermal properties are in the soil. I think that's the big uncertainty. And whether you have, for example, groundwater heat flow. And here it makes sense to work with someone who has expertise in geothermal systems. Yeah.
Okay. If I may, following the same line of questions. First of all, Mike, I really want to say thank you, especially integrating control with the semantic model. I think has been generations of dreams. So it's being integrated. That's really a big deal. I really want to thank you and your group's work. Especially at the end, you mentioned how digital twin is being kind of continuously updated, right? I still remember over about 10 years ago, there was this big rush to automatically calibrate NH plus model, right? And very soon people realize mathematically it's a weak problem because you have less measurements compared with parameter dimensions, right? So I think for Modelica model, you actually have even more parameters because a lot of times it's a dynamic situation. So any thoughts along the direction of kind of understanding the available data and the limitation of the available measurements in terms of mathematically, can you really fully calibrate, or what is the uncertainty assurance coming from the dimension of the data or the reliability of the data?
That's a good question. And so it's hard to answer clearly here because it's very context specific, but let me start maybe with a detailed model versus a simplified model. And detailed models presumably are harder to calibrate. But at the same time, with the engineering insight, you can probably make assumptions about some of the parameters of the detailed model. And let's say we have a cooling coil, and the detailed model has a conduction coefficient, which is a function of where you can choose to be a function of the airflow speed with some exponent. The simplified model doesn't have that parameter. That doesn't mean the simplified model doesn't have some assumptions about it. But now in the detailed model, at least those assumptions are exposed. And then you as an engineer with the insight can make a judgment, do I need to calibrate that, or can I use a default value or something from the literature? So a lot of I often say we should use a detailed model, but default a lot of the assumptions, but at least they are exposed then. So people can make changes to them if they are needed for the particular application. As if you start with a very simple model, it's just a black box. You don't know what the assumption was about that physical phenomena. The other part, it's certainly calibration itself is the whole research area in terms of how to get space filling data, so you don't have a very narrow calibration and there can a lot of bad things can happen there with parameters that are dependent on each other, and it can burst basically. I think that itself is an open research or a very active research area. The other part that we have to be careful with our models is that a lot of the models that we are using, for example, for heat pumps and chillers, they come from decades ago, so from the years of DOE 1 and DOE 2, with certain performance curves, which are typically polynomials. And if you talk to any mathematician, they always say with polynomials, you have to be very careful because small changes in coefficient can cause huge errors, in particular if you start extrapolation. And now with data identification, you may identify your polynomial coefficients based on a small range, you extrapolate and you get garbage. So in some cases that really ask us to see which models would be most applicable for use in data identification, which are not necessarily the one that we use in energy calculations. So from that point of view, it's really a very interesting and research area that I think needs more work in terms of how do we get to these digital twins in a robust way at the end. In particular, if you want to semi-automate or fully automate in the future, that's going to be a few hard research problems to really address here to do that in a robust way. Because if it fails in 5% of the building, it gets a bad reputation and it's not going to be adopted. Yeah, it's a very good question here. Yeah, I have my reservations here. Yeah.
Then you can switch on. I have a few more.
Yeah.
People have a lot of questions.
So one is on.
How to deal with the variation?
Yeah. So it's question a bit this variation, whether it's intentional. So if you retrofit or exchange a component, and then if you have I think it's question is probably in the context of a digital twin here. So then you would probably have to change the underlying component in the digital twin. For example, if you change it with another chiller in your system. other parts of variation could be because the performance deteriorates, for example, because a heat exchanger fouls, and then you certainly don't want to adapt the model always to this. Always, you basically want to keep track of the model adaptation so that you can identify that your UA value is getting worse, and through that make inference afterwards that this one is caused by fouling of the heat exchanger. So I think it's certainly the digital twin, or what people call is digital twin. In my case, it's really a model that's continuously adapted to the actual building using real-time measurement data. And in some case, if you really have a systematic change to the energy system, then you also need to update the digital twin to represent that new system. So Sankey diagrams, we produce them basically with specialized software here. So we used exported data from Modelica and also from MILP and imported that in software here to create those Sankey diagrams. So that's not automated. They are in the tool that we're using, Symphony. It creates automatically Sankey diagrams, but not at this level of clarity that we wanted to have for the publications. Yeah. Yeah, so the question is what's a similar type of building? So, I mean, the question is really, is the physics and the mechanical system applicable to your particular system that you design? So that's the key part. The model itself, they are parameterized, for example, with load profiles for the building load, and then with data for COP of the heat pump. So you would have to update them, of course, to what you plan to install here and what kind of capacity you have. So it's really the systems that we are using, both the MILP and also the Modelica. It's really not an expert system that automatically calibrates or adapts itself, but it's a system for experts so that you can look into this performance. But you need understanding the domain where you apply them and have training in these technologies. Yeah. So how do you get started with platform-based design?
Maybe you can read the question so online people know which question you're trying to answer.
Okay. So basically, what are the recommendations for students or engineers to get into platform-based design, and where should they start? So there is quite some literature about platform-based design. If you look, for example, for Alberto Sangiovanni Vincentelli, which was one of our co-author of the paper that I cited in one of the slides. So he really was instrumental in starting platform-based design when we was approached by Intel to design the 286 chip many years ago, and then applied that and transformed it to different domains. He has a lot of literature about how to do platform-based design, also designs for formal contracts then. So there's quite a rich body of literature that you can read and to get up to speed. At the end, the hard part of platform-based design is really how do you make these different layers, how fine should they be, and then what kind of method do you use to assess the performance or de-risk the design in this particular layer. So that's where really the hard part is of platform-based design. And how do we get huge degree of reusability, because that's at the end boils down to time that is needed for design. If you need to start from scratch each time with developing component models, it's going to take you much longer than if you have a modularization. You invest upfront into development of those libraries, and then you can reuse a lot of those components from one design to another. And then what's the future of Modelica? Are we at the beginning, middle, or end of usefulness? And what will replace it? For example, Julia. So I can't predict the future, but I think it's still growing healthily. So there's a lot of applications now in a lot of domains that are growing now around Modelica. I think the challenges with designing systems and those systems becoming more complex, it asks for tools that can do the physics and dynamics. It's still the only open standard for equation-based modeling that's around. That's not specific to a tool implementation here. Whether Julia will replace it or not, I don't know. If I would know it, I would probably invest in Julia, but it's too hard to predict. It has very good properties too, but it's hard to understand really where that eventually is going to head, those two implementation, which has some complementary parts and some strengths individually of those. Yeah. And why would I recommend the Modelica Buildings Library versus other? So it's, I mean, I'm the main developer of the Modelica Building Library, so that's one of the big reasons why we are using it. And we developed it over the many years to address the needs that we see for the design of such system here. So from that point of view, I think it's very comprehensive. Other people say this is the best validated and documented library in Modelica, and I think it's the biggest Modelica library or open source Modelica library that there is. And in many cases, it's also compatible with other libraries. So if you see, for example, a heat pump component in a library like XLib, you can combine models of the different libraries. So at the end, it's really question is those components in there that you need. How much does it need to add other components here if needed? Are they documented and validated? So can you trust them? And we also have now support by some of the Modelica tool vendors for the Modelica Buildings Library. So I think it's well suited for that application.
I think you touched on it a little bit, but I wanted to understand more on how you categorize your platforms and how you organize different models within each platform and how you synchronize across the platform, especially for a big project. If you could lay it out simply with an example, I think it would be helpful. Thank you.
Yeah. So I think here it was the first time we did platform-based design at that scale. So the earlier paper that was cited, that was for a very small example where we set it up. We have not automated the data transfer between the different platforms. We looked into it. I think quite some of it can be done, but at that point it was a largely manual process. We also learned we should become more formal in this data transfer, because it's just the human element is a key challenge whenever you have a design team, to make sure that they understand each other, that you work with updated data across these different platforms. It's a bit sequential, because first we did the MILP, and then afterwards the Modelica, and then there was some iteration step, but putting everything into a clear way so they can reproduce every step and keep track of where data come from is really critical. And that's a process that we would love to formalize it a bit more and also build tools around that helps us doing that. I think in other industry like the electronic design automation, there are workflows around platform-based design where a lot of this design is fully automated. For example, for chip design, you don't design them manually anymore. So there's tools around that have been developed for requirement verification, for parameter propagation from one layer to another. And there are libraries developed so that the models are consistent between the different platforms. And here we are at the very early stages of that. So that would all need to be invested in to actually develop that. But I think given our experience here for such systems, it's more than worth it. I think after a few installations, you will probably recuperate those costs. There are also other benefits then, for example, that once you have these predefined components, where again a component can be a subsystem, that opens now a way for high replicability also during construction. And that now makes it more plausible to work toward prefabricated systems and industrial manufacturing of some of those subcomponents to further, again, compress the cost and improve quality. So similar than in prefabricated buildings, question is, can we do that for energy system? And what are those modules and how do we represent them then afterwards in such a platform-based design that's compatible with industrial prefabrication of such components or subsystems? So I think there's a lot of other benefits that we can get out here in terms of competitiveness if we make these upfront investments.
Okay, so it's 4:50, time to end the lecture. Thank you again for Michael for this wonderful lecture. Now we have